This is a walkthrough of the 2019 Chemistry Paper 1 Higher Tier. So question 1, what is meant by the term element? Well, just a simple definition is that it consists of only one type of atom. Make sure you don't say consists of only one atom. It needs to be one type of atom. You could also say that it cannot be broken down into anything simpler by chemical means. On to part 2, atomic number is just the number of protons, and they'd obviously be found in the nucleus of an atom. Part B, we have to work out the relative atomic mass of sulfur. So we've got our percentage abundances, and there's an isotope of sulfur 32, and 95.02% have that mass. Now, what we have to do here is work out the total mass of all of these isotopes. So we're going to add on then the sulfur 33 and 0.76% have a mass of 33. Then we're going to add on sulfur 34 times or multiplied by 4.22. So that then will produce the total mass for, if you like, 100 atoms. Now we want the average mass, so just simply divide by 100, and that gives an answer of 32.1. Be careful here, it's asked to give the answer to one decimal place. Relative atomic mass just means that something is compared to carbon-12. Part 3, how is sulfur 33 different from sulfur 34? Now they do have different numbers of neutrons. I would tend to specify the actual number of neutrons in each one. Now, both of these sulfur atoms have the same atomic number, which would be 16. The 16 doesn't need to be there because sulfur always is 16. It cannot change for sulfur. So that's why, as I said, it can be left out. So if you subtract 16 from 33, you'll get 17 neutrons, and if you subtract 16 from 34, you'll get 18 neutrons. Complete this table. Well, the number of protons in sulfur 32, I've already said, is 16. The neutrons, you subtract 16 from 32, 16. And the electrons in an atom is going to be the same as the protons. It's also 16. Remember, all atoms have equal numbers of protons and electrons. On to then the second part, the sulfur 34 2-. The protons will still be 16 because it's based on sulfur. The neutrons, you subtract the 16 from 34, 18. And now the electrons, notice that the charge is 2-. That means that 2 electrons have been gained. There were 16 originally, plus another 2, there would be 18. Part D, I have to determine the empirical formula of the compound. Now remember, empirical formula is the simplest whole number ratio of atoms in a compound. So what I'm going to do first of all is write down the symbols that are in this compound. We've got magnesium and silicon and oxygen. We've got to work out the number of moles of each one. So the mass of magnesium is 1.8, and to work out the moles I would divide by 24. Silicon has a mass of 1.05, divide that by the mass number, which is 28, and then the oxygen is 2.4 divided by 16. So the moles then will be 0.075. The silicon will be 0.0375, and oxygen is 0.15. So the next thing you do then is divide by the smallest one, which in this case is the 0.0375. So that then will become 1. The magnesium will be 2, and the oxygen will be 4. So the formula then will be Mg2SiO4. Question 2. A part 1. Write a balanced assembly equation for the reaction which occurs when lithium burns in air. Well, the symbol for lithium is Li. When something burns in air, that means it reacts with oxygen, and it's a diatomic molecule. Diatomic, two atoms covalently bonded together. And to form lithium oxide, lithium has a valency of 1. You swap it over to the oxygen, don't need to put in the 1. Oxygen has a valency of 2. You put it after the Li. And then to balance it out, you see we need to put a 2 there and then a 4 over on the left. Okay, part 2. Describe in words and by writing electronic configurations how lithium atoms react with oxygen atoms to form lithium oxide. So this is a metal and a non-metal. The bonding here is ionic. So often this type of question would require you to draw out the ionic bonding, but you have to try and describe it in words. Well, the formula, as we've just done above, is Li2O. So there are 2 lithium atoms and 1 oxygen atom. Now we have to write electronic configurations. So lithium is 2, 1 and oxygen is 2, 6. So you can see that the lithium has to lose 1 electron and the oxygen has to gain 2. So 2 lithium atoms are required and each one of them will lose the outer electron. That means then that the lithium ion, which is Li+, becomes 2. And the oxide ion, which is O2-, it is 2, 8. So explain why lithium oxide conducts electricity when molten, and this applies to any ionic compound, and it has to do with the ions. The ions can move and carry charge. Remember, for metals, it's the electrons or the delocalized electrons that move and carry charge. Okay, on to part B. Write a half equation for the formation of fluoride ions from a fluorine molecule. I'm going to put in the arrow. That shows the formation of. And even if you're not sure how to go about this, you've got to try and still pick up some marks. So we've got to do the formation of fluoride ions. Well, fluoride ions are F-, and these are formed from a fluorine molecule. And a fluorine molecule is F2. Now this needs balanced. So 2 has to go in front of the F-. You can see on the left, this is neutral, whereas on the right, there's a minus symbol and there's a 2 in front. So this side has a total of 2-. That means that on the left-hand side, the fluorine molecule gains 2 electrons. And now the charges on both sides balance as well. Half equations always contain E-. Sometimes they're in the left, as is here, and sometimes the E- goes on the right-hand side. Okay, I have to draw a dot and cross diagram for oxygen. Now, these are the 2 that contain a double covalent bond. So, draw my oxygen. I know there's a double covalent bond, and then each oxygen has 6 electrons in its outer shell. So I've got 1, 2 already, 3, 4, 5, 6, and then I do the same with the other atom. 1, 2, 3, 4, 5, 6. For carbon dioxide, just draw the carbon and then the 2 oxygens. There's a double bond, double covalent bond between the carbon and the oxygens. Carbon has 4 electrons of its own on the outer shells, which you have 1, 2, 3, 4. And again, each oxygen has 6 electrons of its own. On the outer shell, we've got 1, 2 already, 3, 4, 5, 6. 1, 2, 3, 4. And then you've got the 5 and 6. And you can see then that these oxygen atoms have full outer shells of 8. D part 1, just a standard definition. What is meant by the term allotropes? Okay, so that's just copied from notes. One difference between graphite and graphene. Well, graphite is made up of layers, whereas graphene is basically one layer of graphite. And of course, those layers are made up of carbon atoms. E part 1, name the type of bonding in a molecule of oxygen difluoride. Well, these are all non-metals. It's a molecule as well. So the bonding is going to be covalent. And this is referring to the bonding between the atoms. Part 2, we have to write a balanced symbol equation for the reaction here. We've got oxygen difluoride reacts slowly with water. In part 1, we've been given the formula of oxygen difluoride. It reacts with water, which you should know is H2O, and it goes to form hydrofluoric acid. That's a bit of an unusual acid, but you've come across hydrochloric acid, which is HCl. This is going to be the same type of thing, only it's going to be HF. And oxygen gas, which is O2. To balance it, you should be able to see then a 2 is needed in front of the HF. Part F. Then we've got lithium carbon in the form of diamond and fluorine, and we'll have to fill in this table. So we'll do the lithium one. First of all, it's a metallic lattice. There's a giant structure. The forces are bonding broken on melting. Well, the bonding in a metal is just metallic bonding. So that's all that needs to go in there. And then this next part, the particles between which the forces are bonding are acting. So in other words, what particles are involved in metallic bonding? Well, in a metallic bond, you have positive ions and delocalized electrons. On to carbon in the form of diamond. The structure is going to be giant covalent. You can see that the forces or the bonding that's broken is covalent. You don't say giant covalent. Giant covalent is just the structure. And then the particles between which the forces or the bonding are acting, diamond is made up of carbon atoms. So the particles are atoms. And then on to fluorine. Well, fluorine is a simple covalent molecule or molecular covalent, so that's the structure. The forces are the bonding broken on melting. Now, there are covalent bonds between the atoms. They're not the ones that are broken. When you have a simple covalent molecule and it melts, it's the bonds between the molecules that get broken, and these bonds are known as van der Waals forces. Okay, on to question 3 then. Potable water is just water that is safe to drink. And chlorine is added to water to kill bacteria or to kill microbes. Now, the test for chlorine gas is damp universal indicator paper, and it changes to red and is then bleached white. Now, aluminium sulfate is added during the water treatment process to bring together all the small fine particles together, and that makes them heavier, which means then they're more likely to sink. And so the name we give to the aluminium sulfate is a coagulant. B, then we're looking at this method used to prepare hydrated aluminium sulfate. In part 1, what piece of apparatus is used to measure 25 cubic centimetres? Well, when it's just 25, it's not 25.0. A measuring cylinder is used. If it was 25.0, then a pipette or possibly a burette would be used for that. The excess aluminium oxide, well, you can see up here that the aluminium oxide is added until it's an excess, and then the excess is removed. Well, if it's an excess, that means it doesn't react anymore. So you just simply would filter it. Now I have to write a balanced symbol equation for the reaction of aluminium oxide with sulfuric acid. Well, aluminium oxide is going to be Al2O3. Sulfuric acid is H2SO4. Remember, you need to be able to recall the formula of acids. HCl is hydrochloric acid, HNO3 is nitric acid. That will form a salt, which in this case would be aluminium sulfate. The aluminium has a valency of 3, so we swap it after the sulfate, which has to go inside brackets because it's made up of different elements. And then the sulfate has a valency of 2, so the 2 goes after the Al, and water is formed. Now you can see here that you've got 3 sulfates, so you're going to need 3 sulfates over on the left. Now there are 6 hydrogens on the left, we need 6 on the right. Part 4, what does the X represent? So in here, that is water of crystallization. Part 5, why is the dilute sulfuric acid a strong acid? Well, a strong acid is one that completely ionizes or completely dissociates in water. Because you could say solution there as well instead of water. Part 6, what's the effect on pH of decreasing the concentration of a solution of the sulfuric acid? Now, all acids release hydrogen ions in solution. So if something is less concentrated, so if an acid is less concentrated, that means that it will have fewer hydrogen ions in solution. And that's what pH measures. It measures really the quantity of hydrogen ions that are there. So the concentration decreases. There will be fewer hydrogen ions in the solution. That means that the pH will increase because the solution is less acidic and is becoming slightly more alkaline. In part C then we'll have to work out the value of X, which is the water of crystallization. So this again is a situation where we have to work out the ratio. I'm going to write down the formula of the aluminium sulfate. So we have to work out the moles of it and then the moles of the water. Now remember, the aluminium sulfate is anhydrous. It's dry, so after it has been heated. So again, I'll just write that in so you remember that. And to work that out, we use the values that we've got. We've got 12.60 grams of the hydrated sulfate, so that contains water of crystallization, and then after it's heated, the anhydrous is 6.84. So we can get the anhydrous mass. That's straightforward enough. That's 6.84. And then to work out the moles, just simply divide the 6.84 by the RFM of aluminium sulfate. And that's 342, which is 0.02. To work out the mass of the water, we just simply subtract the mass of the anhydrous salt, so after it's been heated, from the mass of the hydrated salt. That difference is due to water being lost. So it's going to be 12.60 minus 6.84, which equals 5.76 grams. That can be converted to moles, so we divide that by the RFM of water, which is 18, and that is 0.32. Then we divide through by the smallest number, which is obviously 0.02. That's a 1 to 16 ratio. So X is 16. Question 4, part A. The block of elements in the periodic table which form coloured compounds. Well, those are the transition metals, or the transition elements. And the colours of these copper compounds, well, copper dioxide is black. Copper solutions are usually blue. Copper nitrate solution, copper sulfate or copper 2 sulfate solution. And then calcium chloride. Now, calcium is a group 2 element, and compounds of group 2 elements are white when solid, and they'll dissolve to form a colourless solution. Part C is a question about chromatography. And the student made an error in setting up this experiment. We have to identify the error. Well, you can see, hopefully, that the baseline is below the level of the solvent. And that will mean that the samples will just get washed off the paper, or they'll just dissolve into the solvent. And of course, what we want to happen is for the solvent to soak into the paper, soak up the paper, and then carry the samples with them. D part 1, have to calculate the RF value for C. So that's this one. And to calculate the RF value, measure the distance to the centre of the spot to the baseline. And that's 1.5 centimetres. And then we divide that by the distance from the baseline up to the solvent front. And that's about 4.5. And that gives an answer of 0.33. RF values are always below 1. So if you get a value that's more than 1, then it probably means you've done this the wrong way around. And then part 2, which of the dyes, or the pure dyes, is least soluble in water? Now, first of all, a pure dye will only produce one spot. So B, C, and D are pure dyes. A is a mixture, so it's got 2 spots. The further the spot travels up the paper, the more soluble it is. Now, the question is asking us about the least soluble, and you can see here that in B, the spot travels the least up the paper. So this is going to be the least soluble. Question 5, part A then. This is a question about displacement reactions of the halogens. And just to read here, we've got bromine, which is added to a solution of sodium iodide. And then we've got another reaction happening where chlorine is added to a solution of sodium bromide. There are reactions occurring in both, so we have to write word equations for each of the chemical reactions. Again, in a question like this, pay close attention to the bullet points. They're vital in enabling you to answer the question completely and getting all of the marks. The equations first of all, so I'm going to do the bromine and sodium iodide one first. Well, bromine is more reactive than iodine, so that's why the reaction occurs. The bromine displaces the iodine. And don't write a symbol equation here, because a word equation is what's required. And then I'm going to do the same thing for the other reaction, chlorine and sodium bromide. Again, chlorine is more reactive than the bromine, so we get a displacement reaction occurring. On to the next bullet point. We have to determine an order of reactivity from the most to least reactive. Well, bromine displaces the iodine, so that means bromine is more reactive. Chlorine displaces the bromine, so chlorine is more reactive than the bromine. So it's chlorine, then bromine, then iodine. Finally, we have to give an explanation for this. Well, halogens react whenever they gain an electron. So it has to do with the ability of the nucleus to attract the incoming electron. And the smaller the atom is, the more able the nucleus is to attract that incoming electron. Or here you can write it as I've done. As we go down the group, then the atom becomes bigger. So that means that the outer shell is further from the nucleus, which means then that there's less attraction between the nucleus and the incoming electron. Of course, you could have written that, as I alluded to a few moments ago, you could have said as you go up the group, the outer shell is closer to the nucleus, so there's a stronger attraction between the nucleus and the incoming electron. On to the last part. So these are chemical tests, and we have to write the formula of the anion and cation present. Okay, white precipitate. We're adding a few drops of barium chloride solution. So barium chloride solution test for sulfates, and you just need to remember that. And again, it's always used in solution form, so it's not solid barium chloride. And be careful here, as I've highlighted or underlined, it's the formula that's required. So sulfate is SO4 2 minus. Now I'm just going to show you the equation, the ionic equation, which happens here. So the barium ions in the barium chloride solution react with the sulfate ions that are in solution. So both of these are aqueous. That means they're dissolved in the water. And when they react together, combine, they form barium sulfate. That is an insoluble white solid. So that's your precipitate. On to part 2. Another white precipitate, but this time we're adding sodium hydroxide. Now, when you add sodium hydroxide to a solution and you get a white precipitate, it is either zinc ions, aluminium ions, or magnesium ions. So the excess hydroxide solution added will hopefully then eliminate a couple of these. The white precipitate remains when excess sodium hydroxide solution is added. So when you add excess sodium hydroxide solution, the precipitate that formed in the zinc solution, it disappears. And the same thing happens with the aluminium solution. So these two get a white precipitate, but then that precipitate disappears in excess sodium hydroxide solution. But with a solution containing magnesium ions, the white precipitate remains. So this here is going to be Mg2+. Again, it's the formula that's required. Part 3, we're adding an acid. A gas is produced. Okay, well, carbonates will always produce a gas when you add an acid. And carbonates and carbon dioxide are related. And you can see here that the lime water goes from colourless to milky. So that means carbon dioxide gas is produced. So the original solid is a carbonate. Finally, a flame test. That's the one with the nichrome wire dipped in your concentrated hydrochloric acid, dipped into the sample, then into a blue Bunsen flame, and the colour is observed. In this case, it's crimson. So the ion which produces a crimson flame is the lithium ion, Li+.